Thanks for the nice introduction, Jacob, and thanks for the invitation and the opportunity for me to give you a talk on my topic. And what I want to say at first is that this work is a close collaboration between the University of Greifswald with Markus Münzenberg with his group and the University of Bielefeld with the group of Günther Reis. And there are several people who contributed a lot to this work, namely Alexander Bönke, which most of you know, I guess. He has been here for the last years and he finished his PhD this summer. And so I think he's on vacation now, so he can't be here. And of course, then you know Timo Kuschel maybe, so he's in some kind of in-between state between Groningen and Bielefeld at the moment, doing all kinds of stuff. And so what I want to talk about is the comparison of the laser-induced and the intrinsic tunnel magneto-Seebeck effect in those two different element systems with in magnetic tunnel junctions. So we have the cobalt iron boron magnesium aluminate and cobalt iron boron MgO. And I want to talk just shortly on these two different methods, just to give you an overview and an introduction to that. And so at first, the laser-induced tunnel magneto-Seebeck effect, the ultimate goal more or less is to utilize the rising heat dissipation in nanodevices. So we want to use this otherwise wasted heat. For example, you can think of heat sensors, for example. And we want to do that with magnetic tunnel junctions, or we do that with magnetic tunnel junctions. And you can think of this magnetic tunnel junction having a Seebeck coefficient. And the Seebeck coefficient of this magnetic tunnel junction depends on the relative magnetization orientation of your two ferromagnetic electrodes. So as you can see, you can either have a parallel or anti-parallel orientation. And depending on that, you have a different Seebeck coefficient, and then you measure a different voltage if you apply a temperature gradient across this MTJ as indicated here with the different colors. And then you can go ahead and define the TMS ratio, and the TMS ratio is over here and is defined pretty similarly to the TMR ratio. And so the tricky part in this experiment is to generate a temperature gradient across these nanometer thick films. And we do this with a modulated laser beam that is focused on top of this MTJ. So this is a basic scheme of the setup, which was used the first time in 2011 with Marvin Walter. At that time, he worked in Groningen and then moved to Greifswald. And now I think he's working at IBM or Intel somewhere near Stuttgart. And so what you basically do is you focus your laser through various optics onto your sample, thus generating a heat gradient across your MTJ. And you can then measure this within this electromagnet here. You can have then pickup coils and so on. And you can control your position with the camera at the same time, so you know that you really are on top of your MTJ. And this is basically the laser-induced tunnel magneto-Seebeck effect. And the other model is the model of the intrinsic tunnel magneto-Seebeck effect, which was proposed within these two work groups. And they basically use the intrinsic Joule heating of the tunnel current without any external heating sources. So that they don't have a laser or, for example, an external resistance strip or something like that. They just push a current through the MTJ, and then they get a temperature gradient, and they use that as a tool to get to this Seebeck coefficient. And the basic formula that they use, or that they developed more or less, is this over here, where you can see that we have a asymmetric and a symmetric part, and the asymmetric part is directly correlated to the resistance, while the symmetric part is directly correlated to the Seebeck coefficient. And they do a really simple measurement. Then they apply a positive and a negative DC current and measure the resulting voltage, the plus and the minus side. And then they do a symmetry evaluation, and those are their results that they basically have. So on the left-hand side, you can see the asymmetric contribution. And if you do a linear plot or a linear fit to these data, you can directly extract, in this case, the parallel resistance over here. And on the right-hand side, you can see the symmetric contribution. Where if you do so this is plotted against I squared now. So if you do a linear fit with this data, you can directly extract the CB coefficients in the parallel case. This alpha, the thermal asymmetry parameter, basically includes all the stack properties and stack parameters and so on. And the third theoretical model that I want to talk about, because I used it, or I use it later on in the evaluation of the data, is the Brinkmann model. So the Brinkmann model basically assumes an asymmetric tunnel barrier, as you can see over here. So this is the asymmetry, the height of your barrier, and the thickness of your barrier. And this model basically neglects influences of your density of states and symmetry filter effects, like you have, for example, in MGO MTJs. So this is why the Brinkmann model is only suitable for the MAO MTJ, because there we measured quite low TMR effects and we don't have any density of states effects. So what you can do with this model is then to calculate those parameters, as I said, the height of your barrier, the thickness, and the asymmetry, via these more or less formulas. And what you basically do is to measure an IV curve, build your DJ, dV, and then you have this second order polynomial plot to your data, and you get the A, B, and C coefficients. You can plug them into these formulas. Over here you can see the A, C, and B down here. And then you get those values from your Brinkmann model. Something to the experimental details. So the stacks were prepared in Bielefeld. This is the basic MTJ that we prepared with manganese iridium on the bottom, and then cobalt iron boron MAO. And important in this case is the composition of your cobalt iron boron electrodes, because you get different CB coefficients for different cobalt iron compositions, but we'll see that later on. And then we do some electron beam lithography to pattern those stacks into MTJs, or actual MTJs. And then you can go ahead and do a laser-induced TMS measurement with the laser on top of the MTJ, and then a subsequent IV measurement in order to, do something with this model of the intrinsic TMS. And the MGO MTJ actually was prepared in at that time in Göttingen, I think. And there you have a little bit, another composition of your cobalt iron electrodes, which will become important in a moment. So another tricky part in these experiments is the temperature gradient across your barrier, because this more or less defines your CB coefficients, which you want to know, of course, or which you want to calculate. And therefore, you need to do, at the moment, COMSUL simulations, because you can't do any experiments to measure this temperature gradient or this temperature difference across your barrier, unfortunately. And therefore, you have to plug in some thermal conductivity of your thin barrier, for example. So at this here is an example of the thermal conductivity of MAO that we chose for this case. And we included a high error range in order to account for this uncertainty within this thin film regime. And another thing that you can see is that the temperature difference across your barrier is highly dependent on the beam waste of the laser spot, for example. So usually we measure with something like 5 micrometer beam waste. And you can see that the temperature difference is, it's really dependent on your beam waste over here. So you can, if you're only a little bit off, say 4 or 6 microns, you're at something like 140 to 75% in comparison to the 5 microns that we usually use. And this is quite important, because in this work it was stated that the thermal conductivity of the MGO that was used, so this is the bulk value of MGO, the thermal conductivity. This is thin film thermal conductivity in MGO, and this is the newest value that was published for the thermal conductivity of MGO. And this is actually, as you can see, one order smaller than the values used before in the publications before. And now we can see some results. So on the top left side there's the MAO MTJ, then in the middle the MGO MTJ. And as you can see, we have nice switching behavior in case of TMR and TMS effects, and we get effect ratios for the MAO MTJ of around 34% TMR. As I said, pretty low, and obviously no coherent tunneling, which is why we can use the Brinkmann model later on. And then you get a TMS ratio for this kind of structure of about 3.3%, which is pretty much comparable to the literature values. And as I said, the cobalt iron composition is important over here. And for the MGO MTJ, you get something like 200% TMR, which is pretty good, and a TMS ratio of 23%. And now you can see that the composition of this cobalt iron plays a big influence on this, or has a big influence on this TMS ratio. So you get 23% with this different cobalt iron composition as suggested in the literature by the Heiliger group in Gießen. And another thing that you can see in the MIO case, we have a nice linear behavior of our Seebeck voltage with the applied laser power, so we can go up to 150 milliwatts and see a nice linear behavior of the Seebeck voltage. And also you can see that the TMS ratio more or less stays constant around 3.3, 3.4, 3.1 or 2 sometimes. And with the aforementioned temperature difference across the barrier, you can then go ahead and calculate your Seebeck coefficients. So in the case of the MAO MTJ, we get something like minus 150, minus 160 microvolts per Kelvin for the parallel and antiparallel case. And in the MGO case, we have something like 1000 or so. That is still with the old value of thermal conductivity for the MGO. And due to the fact that the thermal conductivity of MAO has such a large error, the error bars or the error within these values is something like 140 microvolts per Kelvin. All right, so then a short thing about the Brinkmann results. So you can see that we get for the barrier thickness something like 1.7 nanometers. And if you remember, the nominal barrier thickness that we wanted to have is 1.8 nanometers, so this corresponds quite nicely to the things that we expected. And if we then go ahead, so those are the measured IV curves now, and from that we can go to the intrinsic TMS results. So on the left-hand side is the MAO MTJ, on the right-hand side the MGO MTJ. And as you can see, the measured blue curves are parallel and antiparallel. In this case, the asymmetric contribution, and this is at high currents, it is deviating from the linear or the expected linear behavior of our asymmetric contribution. We can then go ahead and fit this with a linear fit if we go to low currents, for example, and then extrapolate this linear fit, and we can calculate the resistance via the proposed formulas of Zhang and Teixeira. And then we get resistance results that are close to the resistances that we got from the TMR measurements. So that is all good up to now. But if we go to the symmetric part, we see more clear and more distinguished deviation from this expected linear behavior. So we have clear deviation from this linear behavior, and we can then zoom in these graphs, both of them, and fit the first part of the curves with the linear fit. And then we extend the linear fit to the whole range. And as you can see, this doesn't really, it doesn't really describe the curves that well. But nevertheless, you can go ahead and extract the slope of these curves or of these linear fits and calculate the thermal asymmetry parameter and then extract the Seebeck coefficients. And if you do that, you end up with something like this. So on the upper part is the MAO MTJ, where we get Seebeck coefficients looking like this, and which are not only in absolute value but also in the sign different than what we got from the laser-induced TMS measurement. And in the case of MGO MTJ, this looks pretty similar, so we don't come close to the TMS ratio that we obtained with the laser-induced method. And what we now want to do, or what we did is to find a different explanation for this symmetric contribution, because well, it doesn't really look like we have an intrinsic TMS in these kind of samples. So we went ahead, and you can then use the Brinkmann model again in case of the MAO MTJ. And as you can see, this red area is now the Brinkmann model with the typical error of 10%, and you can describe your symmetric contribution very well, very good with your Brinkmann model. And you can go ahead and simulate that, for example, for a barrier asymmetry of 0 EV or plus, or the other way around. And you can see that your symmetric contribution is solely influenced by the barrier asymmetry given from the Brinkmann model. So the symmetric contribution in this VI curve that the Zhang and Teixeira group proposed to be the intrinsic TMS is just caused by this by this asymmetry of your barrier that you get when you deposit your samples. And those results were published a few weeks ago in PRB, and you can have a go and learn something new maybe, and read it and cite it, of course. And so the new ideas that we have, or that we want to do now, is to do some thickness variation of our barrier. And the first results came in a few weeks ago, and they are looking like this. So we have measured that for several heating powers, and you can see a clear maximum at around 2.6 nanometers of barrier thickness. So it's still a bit unclear why we get a maximum at this value. So you can see that this is something around 3 to 4% at all over the whole range, and then suddenly at 2.6 it shoots up to something like 8% or something. And we prepared some more samples and we want to get an idea why that is and why we have this maximum over here. And also the theorists are working on that, and hopefully we can learn something. So to conclude, you have seen TMS measurements and TMR measurements on MAO and MGO MTJs. You have seen that the symmetric contributions of our IV curves are deviating from the expected linear behavior, and that the model of the intrinsic TMS is not accurate or gives no reliable results in comparison to the laser-induced measurements. And we have seen distinct maximum of the TMS ratio, which we will investigate in further studies. Thank you for your attention.
Thanks, Torsten. Are there any questions?